Hello. I heard from a fair number of you that you're a little lost about a few things. So just real fast, I'm going to go ahead and we're going to cover the basics of everything we've learned so far this semester. So no example problems, so we're not going to be building skills. So there still might be some discrepancies in what you can understand and actually do. But we're going to start by making sure the basic understanding is there. And then if you have specific questions about how to do the problem solving, that will come out as we run more example problems. All right, so what we're going to do is we're going to cover the idea of position and displacement, velocity, acceleration, then we're going to do one-dimensional kinematics, and then finally two-dimensional kinematics. With a little brief interlude about vectors. So the first thing is position. Position is how we describe where we are at a given moment in time. The example I used in class was the football field, because it has those nice lines on it that are already numbered. Except this is how football does it, American football. So we could say that I am starting in a position, I'm standing at the 0-yard line, but then I end up at the 30-yard line, but then I end up at the 50-yard line, and now I'm at their 30-yard line. Okay, that's confusing. That's weird from a mathematical standpoint, from a physics standpoint. So we might instead call it this. We might call where I start 0, and then everything else is positive. So I go from the 0-yard line to the positive 30-yard line to the positive 50 to the positive 70-yard line. Okay, that could also work. But I could also do it like this. Call the dead center 0, which means now positive is to the east and negative is to the west. Why not? In this case, I start at the negative 50-yard line. I then go to the negative 20-yard line, then the 0-yard line, and then the positive 30-yard line. It doesn't actually matter. As long as you are consistent within a problem, where your 0 is doesn't actually matter. Because it's usually not actually position that we care about particularly, but displacement, the change in that position, which has a positive or negative built in. So if, for instance, I go from the negative 30-yard line to the positive 30-yard line, my displacement, what I actually care about, is positive 60 yards. I ran 60 yards east. Or Mrs. Saslow then tackles me, I fumble the ball, she grabs it and runs off down the other direction. She starts at the 30-yard line, ends up at the negative 30-yard line. Her displacement was 60 yards to the west, or negative. Now, there's this idea of velocity, which is how fast you're going. All right, that's nice. Average velocity would be like when you're taking a road trip. If you're trying to figure out, well, how long is it going to take me to get there? You're not actually going to calculate, okay, well, I'm going to go this fast while I'm here, this fast while I'm here, and I'm going to stop for an hour, and then this fast while I'm here. You're going to go, well, it usually takes me roughly 4 hours, 5 hours, whatever it is to get to where I'm going, and it's this far, so I'm going to divide those two, and that's my average velocity. It doesn't take into account those times when you're going faster, those times when you're going slower, those times when you're not moving at all. It doesn't take into consideration of the path that you take. Average velocity just takes starting point, ending point, time. Now, the instantaneous velocity is the how fast are you going right now. This is what Highway Patrol looks at. So when they give you a ticket, they don't say, well, your average velocity was too high. It's because your instantaneous, your right at that moment velocity was too high. So here we got a picture of Usain Bolt running ridiculously fast. His instantaneous velocity is very, very high while he's taking this particular picture. The instantaneous velocity will tell you what your velocity is at that moment. So if you speed up, the instantaneous velocity will go up. If you slow down, the instantaneous velocity will slow down. This is what we graph. This is what in physics we usually care more about. All right, now if we're going to compare them, let's talk about the tortoise and the hare. How the heck did the tortoise win? Well, according to the story, it's because the hare was going so fast that he got cocky, took a nap. While he was sleeping, the tortoise passed him by. So the tortoise had a higher average velocity, even though his instantaneous velocity was usually much lower than that of the hare. But since the hare was going so fast and then not moving at all, the hare's average velocity ends up being quite low, even though his instantaneous velocity was quite high. So here we have the speed of the tortoise graphed as a function of time. Nice, easy, constant. Let's see what the hare was doing. Well, the hare took off like a shot, got way far ahead of the tortoise, started going at its max speed for a while, saw a nice tree, slowed down, took a nap. At some point later, woke up and went, oh man, that's right, I'm in a race, and took off again. So even though the hare's instantaneous velocities were sometimes higher than that of the tortoise, sometimes lower, the hare's average velocity, showed by the dotted line, is lower than the average velocity of the tortoise. So the tortoise won, even though the hare can run faster. All right, now there's the idea of acceleration. If displacement is how much your position changes, if velocity is how your displacement is changing over time, your position is changing over time, acceleration is how your velocity is changing over time. The rocket is not going at a constant speed. It is getting faster and faster and faster and faster and faster and faster and faster. The bowling ball is going at a constant speed. It's just going, it's coasting. So although both are moving forward, they have different accelerations. The rocket has a large positive acceleration. The bowling ball has the acceleration of 0. When you slam on your brakes in your car, you have a large negative acceleration. In all 3 instances, you are still moving forward. In all 3 instances, your velocity is positive. Your displacement is positive. But how your velocity is changing is different. The bowling ball's velocity doesn't change. When you're in your car braking, your velocity is getting lower and lower and lower. But the rocket, the velocity is getting higher and higher and higher. All right, so we can graph these things. And we've spoken about these relationships. Sorry, the picture is so blurry. But if you take the slope of, say, the position graph, you will get the instantaneous velocities. So let's look at the top row. You have an object whose position is not changing. Okay, the slope of that line, well, it's a horizontal line, the slope is 0. So the instantaneous velocities are 0. All right, now let's look at the second row. The position is going up at a constant rate. It's moving forward. All right, so if I take the slope at the beginning and the middle and the end of this, I get the same number because the slope of a line is constant. I graph that. My instantaneous velocities are unchanging. We're being like the tortoise. So my velocity line is now horizontal because my speed is not changing. Third row. My position changes a little bit, and then it starts changing more. And then it starts changing more. And then it starts changing more. With each subsequent second, I travel a further distance. So if I take these slopes, I end up with a very small slope, and I start with a small slope, and I end with a quite large slope. When I graph that, I get that angled line for velocity. The velocity, like the slope, starts small and ends up large. Now I can do the same thing with the velocity graph. The slope of the velocity graph will give me acceleration. In this class, our accelerations will always be constant. So top row, my velocity is 0, and then it's 0, and then it's 0. So the acceleration is 0. Second row, my velocity is 5, and then it's 5, and then it's 5. My acceleration is 0 because the velocity didn't change. Third row, my velocity is 0, and then it's 1, and then it's 2, and then it's 3. My acceleration is 1 because my velocity changes by 1 each second. Now, using the graphs, we can also go the other direction. If you find the area under the curve, so for instance, the area under the curve of a velocity graph, you see that here shaded in purple. If I take that area by splitting it up into the red rectangle and the blue triangle, finding the areas, adding them up, that gives me the displacement. So I don't know where I started, I don't know where I ended, but I do know that I ran that far and in this direction. If I do that same thing for an acceleration graph, I get the change in velocity. It doesn't tell me my initial velocity. It doesn't tell me my final velocity. It tells me how the velocity changed. Just like the velocity graph does not tell me my initial position or my final position, it tells me how my position changed. All right, so now we get to kinematics and these glorious equations. The first 3 are equations that the AP does not expect you to have memorized. It will be on your equation sheet. The last one, however, is not on your equation sheet, but it's super helpful, so I would just memorize it. Whenever you're doing a kinematics problem, we're talking about instantaneous velocities. We're talking about positions and displacement. So I would always start by drawing a picture, even if it's just in your head, and label it. All right, here's the initial position, here's the final position, so here's my displacement. I know that the initial velocity is this, my final velocity is a big question mark though. Here's the time. Label everything. Everything you know, you don't know. Then use that list to make, or to choose, I should say, your equation. Choose your equation, do not plug numbers in, rearrange it. Solve it algebraically first. Then plug your numbers in and get an answer. Exception there is if your velocity is 0, just plug that in right away because it's going to make your math easier. All right, so example time. Mr. Sazzo is on his rocket skates. He traveled 30 meters forward while speeding up from 5 meters per second forward to 25 meters per second forward. What was his acceleration? All right, so the things I know: initial velocity, final velocity, displacement, and I want acceleration. There is only one equation that has those 4 things. So choosing should be easy. Bam, there it is. V final squared equals V initial squared plus 2 times A times delta X. I am now going to rearrange. So first I subtracted V naught squared on both sides. Then I divided by 2 delta X on both sides, and that gives me my A equals equation. Now I plug in my numbers and simplify. All right, so that's 25 squared minus 5 squared, so 625 minus 25, divided by 2 times 30, so 60. Well, 625 minus 25 is 600. 600 divided by 60 is positive 10. In this case, it's acceleration, so positive 10 meters per second squared. Every second, my velocity changed by 10 meters per second. Every second. All right, now I can do this exact same sort of thing, but in the y direction. I don't have to be in the x direction. I can also do it for going up and down. Things to consider here. Let's start with the guy dropping the ball off the cliff. We're going to treat this exactly the same as we would treat the x direction. The only thing we've got to remember is that sometimes my delta y is going to be positive, sometimes my delta y is going to be negative, sometimes my delta y is going to be 0, depending. So for instance, here on the left, there I have my first displacement for the first second. That's a negative displacement. From the beginning to the second, negative displacement. From the beginning to the third second, that's a negative displacement. From the first second to the last second, that's a negative displacement. So when I'm dropping, I will know that the initial velocity is 0, as it usually is at the top, and my delta y's are always going to be negative. So even though I might tell you, yeah, the cliff is 5 meters high, you'll have to put in -5 for your delta y, because this ball is not going up, it is going down. Now, it is going up for the gentleman on the right. So there's my first displacement. That is a positive displacement. Then in the first beginning to second, positive displacement, positive displacement, positive displacement, still a positive displacement. So the ball is going down now, so its velocity is negative, instantaneous velocity is negative. But the overall displacement is still positive because it started low and now it is higher than that. Displacement is still positive, displacement is still positive, displacement is 0 because now it is ending at the same spot it started. All right, so things we can label. As it is traveling down for the gentleman on the left, that means the instantaneous velocities are going to be negative. At the very beginning, my delta y is 0 because it hasn't gone anywhere yet. And at the end, my delta y is going to be negative height of the cliff. Gentleman throwing it up, instantaneous velocity is positive. When it reaches the top, the y velocity is going to be 0. The delta y will be positive h. And then it's going to start to fall with a negative y velocity, instantaneous. And then once it gets to the same height, its delta y is now 0 because it's right back where it started in terms of y direction. All right, now, before we jump into projectile motion, just a reminder about the trigonometry involved with vectors. We haven't used the word vector particularly, but a vector is anything that has a magnitude and a direction. So our displacements, our velocities, our accelerations are all vectors. You can have a net vector, or you can have component vectors. So when I kick a soccer ball at a net velocity of positive 6 meters per second at an angle of 23 degrees above horizontal, my net velocity is 6 meters per second at 23 degrees. Okay, but I usually don't want my net velocity, but my x velocity and my y velocity. So in this case, my x velocity would be 6 meters per second times cosine 23. My y velocity would be 6 meters per second times sine 23. Again, degrees. And the way we got those equations, I put them up top here next to my head now. This shows you how it works. So there, you know that sine theta is going to be y direction divided by net. I multiply both sides by net, and that gives me the equation that I have down there. I know that cosine is going to be my x direction divided by net. I multiply both sides by net, and it gives me that mx equation that we have written down there. All right, and then tangent. We don't often use that, but it's important to remember that it is, in fact, there. All right, projectile motion. Here's a picture. It shows you basically everything you need to know. But here's the things to remember. You always start by splitting your net velocity into x and y components. So in this picture, the green initial velocity is the net velocity, magnitude and angle. You would split that into a Vx and a Vy using the equations from the last slide. You would then solve for time, which time depends on what you're looking for. Air time is going to give me the maximum range. It is going to give me a delta y of 0. It is going to give me final landing, crashing into the ground velocity. But half time, half the air time, that's going to give me a delta y that equals max height. It's going to give me a delta x that equals half my range. It's going to give me a y velocity of 0. The x velocity is constant throughout all of this because it doesn't have an acceleration. When I throw something, it's not a rocket. So forwards, it is just coasting. The only thing that's changing its velocity is gravity. So as it's going up and down, velocity is changing. But the moving forward bit is constant. All right, this is everything as far as raw content is concerned. The next step is, well, can we actually use this knowledge to solve problems? Please email me any questions that you might have about how to do that. And next week, that's basically all we're doing, is running example problems. All right? I hope you found that useful. Have a good day.